We're going to start fresh now with a new chapter. This is chapter 10, the interior of stars. And this is something that's exciting for me because in my research, I've done a lot with stars and star collisions, and I like to understand how stars move and respond. And to just do a star collision, you need to make a model of a star to begin with. So it's something that I've thought a lot about over the years. And we're going to hit upon the main equations today, really, that are necessary to describe stars. And to preview this, the first thing is going to be the equation of hydrostatic equilibrium, right? Hydro makes you think of fluid. Static means that it's not moving around. Equilibrium means that similarly, it's not moving around. And so stars, to a good approximation, are just sitting there. If they're not rotating, they'll just be nice spherical balls. And today we'll learn the equation of hydrostatic equilibrium, which tells us how pressure or buoyancy forces are balanced by gravitational forces. For today, I only asked you to read section 10.1. Section 10.2, we'll talk about equations of state. And so the equation of state will give you the pressure as a function of things like density or temperature, or density and temperature and composition, right? And so together, the equation of hydrostatic equilibrium and the equation of state allow you to describe the interior structure of a star. So we're actually going to derive this equation of hydrostatic equilibrium in the plane parallel approximation. And this is something that I actually have all of my research students do when they're starting to learn about this hydrodynamic code that we use. And in particular, what this means, the plane parallel approximation, is that we're not going to think yet about a spherical situation like a ball of gas. We're just going to think about an atmosphere where we're on the surface of the Earth maybe, and we're not worried about the curvature of the Earth. We're looking at a small enough length scale that we can pretend the ground is flat, horizontal everywhere, and that you just have horizontal layers above it. So if you like, you can think about zooming in on a small portion of a spherical star, small enough that the curvature is not important. And so this will be what we call the z-axis. And there's going to be some slab of gas that we're considering. This slab is going to have a height dz. So the slab at the base of it will be at a location z. And then at the top of the slab, we have the position z plus dz. And the area of this rectangular box is going to be called A. And the idea is that as you go upward, the pressure could change. Like just as you go upward in the air in this room or outside, as you go up higher and higher, the pressure gets less and less. So we'll call the pressure on the top part of the slab P plus dP. And then we'll call the pressure on the bottom just P. So this is pressure P down at the bottom here. So at the location Z, the pressure is P. At the location Z plus dZ, the pressure is P plus dP. And we're saying it's uniform pressure in the X and the Y directions that are perpendicular to the Z direction. And so the idea here is, you've got gas everywhere. You've got gas above this slab. You've got gas down below this slab. And this is a slab of gas. The mass of this slab is going to be denoted by an M. And so what we're going to do next is we're going to talk about what is necessary to have an equilibrium, that is to have the gas not move, right? If for whatever reasons, the air above it, the gas above it was evacuated, a vacuum, then there was some pressure down here. Well, there'd be, the gas would just be pushed upward because it'd be pushed up into the vacuum. That's not an equilibrium situation. You want to find a situation where the force is balanced. And there is implicitly here going to be a force that is going to be in the downward direction. the force due to gravity, right? So you can think of this as being, you know, inside of a star or the surface of the Earth, but the downward direction on the board is the direction in which gravity would pull something. And that's going to end up being balanced by the pressure difference force that is pushing upward. So in equilibrium, what we want to do is we want to set the net force on this slab of gas equal to, well, in general, we know from Newton's second law that the net force would be mass times the acceleration. We want it to be 0 in equilibrium because that's what this means. We don't want things to be moving around. So what we're going to do is we're going to make a free body diagram, just like you did back in Physics 101 or Physics 110. And this is a free body diagram for this slab of gas. And so there are 3 forces that I am going to be considering on it. 2 of them are contact forces. There's the gas on the bottom of the slab, which is pushing it upward. And so that force is going to be P times A. Remember that pressure is defined to be a force per area. So if we take the pressure on the bottom and we multiply by the area on the bottom, we get the force pushing upward on that slab. Now the gas on the top of it is going to be pushing down on the slab. And so that is going to be P plus dP, that's the pressure on the top, times A. Now I drew this arrow a little bit shorter than this other arrow on purpose. And the reason for that is I'm thinking about like air in this room, for example, or on the atmosphere of the Earth. And I know as I go upward, the pressure gets smaller. And so that means this dP quantity, at least in that scenario, would be a negative quantity, right? If the pressure were getting bigger for whatever reasons as you went upwards, then dP is positive. But it's getting smaller in my mind, which is why I drew the arrow a little shorter here. And now there's one more force. It's a long-range force. It's the force of gravity that I'm speaking of. And so we have the mass of the slab multiplied by the local gravitational field, G, mg. And that is going to be downward as well. And so the idea is that in equilibrium, these force vectors should all cancel one another. These 2 downwardly pointing ones should be equal in magnitude when you sum them up to the upwardly pointing one in order for you to have the net force equal to 0. So let's go ahead then and erase the top of this board and write out the equation for having this net force be 0.
Professor, I have a quick question.
Yeah, please.
The P plus dP times A force pushing down is due to the slab of gas that's above?
Yeah, that's right. So just think of this as gas throughout this whole region. And there's nothing special about the slab. It's not like there's a physical boundary there. It's just in your mind, you've partitioned this slab out from all the rest of the gas. And so the gas on the top is pushing down exactly as you said. Yeah, thank you. Other questions and comments? All right, so I'm going to write out then the second law as an equation with the help of that free body diagram. The net force, well, there's the downward force of gravity minus mg. There's the upward force of pressure from the gas beneath the slab. And then there's the downward force of pressure from the gas above. And the minus signs remind me that they're downward forces. Now, if you look, this PA right here cancels with this P times A, leaving behind just the minus dPA. So it's going to be pressure differences that are important, right? It doesn't matter if the pressure on the bottom is an atmosphere or a million atmospheres. It only matters how much the pressure changes as you go from the bottom to the top. And so let's go ahead and write out the more simplified version. This is minus mg minus dp times A. Now, the next thing that I'm going to do is I'd like to try to understand how, as I change my vertical positioning, Z, how the pressure changes. And so what I'm going to do is think about that dP there, and I'm going to be trying to turn it into a dP dZ, the derivative of pressure with respect to height or elevation Z. And so I divide both sides of this equation by dz. I'm also going to bring the second term that's on the right over to the left and divide by A. So I still have my minus mg. I have divided by A, and I've also divided by dz. So what I've done here is I've solved for dP and divided by A. And when I say divided by A, of course, I divide both sides of the equation by A to maintain the equality. Now, I want you to think about what the geometric meaning of A times dz is. It is the what of the slab. When you figure it out, let me know. It is the volume. Yes, I hear a couple of you saying that, right? Because remember, A is the cross-sectional area of that slab. dz is its height. So the product of those two things is the volume of the slab. So this is the volume of the slab. And what is the mass of the slab divided by the volume of the slab? What's that known as? That is the density. Right? And so this allows us to recast this equation in its more familiar form, that dP dz is minus g times rho. Rho is the density. And so what we've used here is that rho, the density, is mass over volume. This is the equation of hydrostatic equilibrium in the plane parallel approximation. And what it's telling you is that as you go up to different elevations, it tells you how quickly the pressure changes. How quickly the pressure will change will depend on the local gravitational field. You can, if you like, for the sake of understanding this equation, think momentarily at least about G as being 9.8 meters per second squared, right? At least if you're near the surface of the Earth, G would have essentially that value everywhere, approximately. Inside of a star, that G value could be a function of position, more generally speaking. But whatever position you're at, it'll have a G value. You multiply by rho, slap on a minus sign, and that tells you the rate of change of pressure with position. So that, I said, was the plane parallel approximation. That's when you just have flat slabs on top of flat slabs, right? And you could think now about many slabs being stacked on top of one another, each one of which would satisfy this equation that we were writing down. And so if we wanted to know the difference between pressure at one location and then some other location far above, you could integrate dP from the bottom to the top to get the change in pressure, delta P. Now, in stars, we have, to a good approximation at least, spherical symmetry, especially if the star isn't rotating. Even the sun, which does rotates around on its axis, but even that rotation doesn't destroy the spherical symmetry very much. And in spherical symmetry, this equation of hydrostatic equilibrium looks pretty much the same. The only thing that changed here is we went from Z to R. And so, you know, this scenario that you'll think about in the back of your mind now is that instead of having plain parallel slabs, you have spherical shells. And the shells could be separated by some infinitesimal distance dr. That's what I tried to write in there between the two, dr. And so this tells you how the pressure changes as you go from one shell to the next shell, a distance dr out further. And G here is going to be a function of position. And as is rho going to be a function of position, because stars get denser and denser as you go in towards their centers. What do you think G is, the gravitational field, at the very center of the star that's spherically symmetric? Zero. Right. Because by symmetry, the mass of the star, let's say you put a little test object at the center of the star and you ask how it's being pulled by all the other mass in the star. Well, the mass over here is going to pull that test object that way, but there's going to be mass on the other side that counteracts it and pulls it the other way. There's going to be sort of forces pulling that object in all directions, but for any one force you have, there's going to be a counterpart which is exactly opposite from a source on the other side of the star that's equidistant away. And so G is equal to 0 by symmetry at the center of the star. And then as you go out and out and out, G becomes more and more and more. And we'll talk in a moment about how you calculate G, what you need to know to calculate G. In fact, why don't we write that down now? This is equation 10.6 from your reading for today. That's the equation of hydrostatic equilibrium in the case of spherical symmetry. And so next what we're going to do is we're going to talk about how you would locally be able to figure out what G is. So G, it's an acceleration due to gravity. And remember, an acceleration is a force divided by a mass. And the force here is the force due to gravity. And so it's going to be Newton's gravitational constant times the enclosed mass over the distance from the center squared. Remember that a gravitational force is minus G m1 m2 over r squared. However, capital G, the way we define it, is as a positive quantity. Just like, you know, lowercase g, I meant to say, it's a positive quantity. Just like when you have 9.8 meters per second squared, lowercase g, that lowercase g is positive here. This lowercase g is also positive. The minus sign has already been taken into account in the equation of hydrostatic equilibrium itself. What is this m sub r thing? The subscript r is a reminder that this enclosed mass, m sub r, is a function of position r. So this is the enclosed mass at radius r. So here's my star, and maybe I go out, there's the star. It has a full radius capital R, just so you realize that that's where it ends. But I'm somewhere in the middle of it at a radius lowercase r. And then I imagine making a sphere of radius lowercase r. And however much mass is inside of that sphere, that's what I'm calling m sub r. Now this point right there might be the location of some test particle m2. And remember I said the force of gravity was g m1 m2 over r squared. But to get an acceleration, you divide by the mass of that m2. And so that's why there's only one mass here. It's because we have an acceleration, not a force. Now, this is a beautiful result that Newton first proved geometrically. You can show it also with calculus. He did a beautiful geometry argument to show this. What happens is that all of the mass outside of radius r has a net effect of 0. I know many of you haven't had the upper level electricity and magnetism course, but you would see that same kind of thing in there as well. But in any case, in electricity and magnetism, let's say you had a charged ball, not filled in the inside, but just on the surface of the ball you have charges. Then if you put a charge in that ball, there's no net Coulomb force on it. Now remember, Coulomb force varies like 1 over r squared, just like gravitational forces vary like 1 over r squared. So the same kind of things you may have learned in some other context are actually applicable here. And all of this mass on the outside, outside of this radius lowercase r, the net effect of it is to have no net force on that little test particle there. It's only the matter interior to it which will end up affecting the force on that object and how it accelerates. So to just beat this idea home, let's imagine you just had a spherical shell of mass and you put a test mass inside of it. So this is all hollowed out except for mass along this shell. You put a test particle inside of it. Which way does it accelerate due to gravity? No way. There's no direction. Even though it's closer to this side, and you might think, oh, it's going to get pulled in there because it's close to it, there's not as much mass that is close as there is mass that is far away. And although I haven't proven it to you, I'm trying to give you a plausibility argument for explaining why the pull towards that direction is balanced by the pull in this direction. And likewise in that direction, that it all balances out. There's no net force on that. It's only the mass inside that matters. So that's what this is saying. G, mass enclosed over radius squared.
Professor, I have a quick question. Everything enclosed by little r is going to have a higher density than the stuff outside because it gets denser closer to the core, right?
That is true. And in fact, we'll be able to see that once we connect pressure to density. We'll be able to see that pressure goes smaller as you go outward, and that will mean density also gets smaller as you go outward. Other questions and comments?
Say we just have the Earth. We feel 9.8 meters per second squared at the surface. If we were to go farther into the Earth, there's less mass enclosed. So does that mean acceleration due to gravity gets smaller?
It does eventually. It kind of depends on, I think it gets bigger for a while and then gets smaller again. But it depends on how the mass is distributed, right? Because this is not how the Earth is actually modeled. But to explore the basic idea that you have here, let's imagine that we had a planet which had constant density, just for the sake of argument, right? We know that that's not the way the Earth is, that it does get denser as you go deeper. But because we don't have a detailed model of the Earth readily available to us here and a computer to analyze, yeah, we're just going to simple model constant density planet, right? So in this case of a constant density planet, m sub r would be the volume times the density. And so if I wanted to know what g was as a function of position, it would be g times 4/3 pi r cubed rho over r squared. And notice that this scales proportionally with r. And you could write, figure out the proportionality constant is 4/3 pi rho g. And so if I plotted g versus position, it gets bigger until you get to the surface of the planet. Here's my planet of radius capital R. And then once you go outside of capital R, there's no additional mass that gets enclosed. So at that point, it starts to fall off like 1 over r squared. So this G proportional to R is only when you're inside the interior of the planet, when R is less than capital R. For R greater than capital R, then you have m sub r is the mass of your planet, and so it then falls off like 1 over r squared. Does that help?
Yes.
In general, let's say you didn't have rho equal to a constant. Let's say that rho was some known function of position. So what if the planet were not just rho equal to constant? Let's take rho as some function of r. So it's still not arbitrary because it's spherically symmetric, but it's more general than saying rho is constant. How would you get the mass enclosed inside radius r? Well, what you would do is you would take rho times 4 pi r squared dr and integrate it from the center to the location where you're trying to calculate the mass enclosed. And so the idea of what's going on here is that 4 pi r squared dr, this is the volume of a shell of radius r and thickness dr. And so if I draw this, maybe here's our planet of radius r. I'm somewhere inside of it. There's a shell. The shell has thickness dr. And what I want is the volume of this little shell. I say little because it's thin. It's thin enough that the density does not change significantly as I go from the inside of it to the outside of it, because it's only infinitesimally thin. It has a thickness dr. And 4 pi r squared is, of course, the surface area of that shell. And if I multiply the surface area by the thickness, I get the volume. You can kind of think about, you know, if I multiply something that has a cross-sectional area A by a thickness dz before, that gave me the volume. And here it's the same thing, except for it's all curved around. And you don't need to worry about the curvature because dr is infinitesimally small. If it were a delta r, technically you'd need to take the volume of the outer surface minus the volume of the inner surface to get what's in between. If you do that, you get some answer that's accurate to higher orders and an expansion with dr in it. But we only need the lowest order term in that expansion. And that lowest order term is the area times the thickness. That's the volume of the shell. You multiply that volume by the density, you get the mass. So you think of this whole thing here as with the d rho in it as being a dm, the mass of a shell. And if you add up by integrating all the shell masses from 0 out to the r that you care about, that r in the upper limit of integration is the same r that's in the subscript of m there. And so you would get the mass enclosed out to that radius. Now, this last equation that I wrote down, which is the integral way of calculating the mass enclosed inside a radius r, can be written not in integral form, but if I imagine differentiating both sides of that equation, what do I get? dm sub r is 4 pi, let me actually write it this way, rho times 4 pi r squared dr. And the logic for this last equation here, and is the same logic as what I was saying here. It's in fact even a little bit simpler, because I had to go through all this argument for why this was the mass enclosed inside of a shell. And then there was one more step. I said I had to integrate up all the shells. Here I just do everything other than that last integration up. So really, I suppose if I wanted to be very careful with my notation, which I do, I really should not write dm here. I should write d capital M sub r. That would be a consistent way to talk about the mass of that shell. That is what the integrand here is of the integral that I'm doing. I'll just label this diagram here by drawing a line from this shell all the way over and around to here, because I want to make sure that it's clear that that picture is related to these words. The volume of a shell, the word shell has two L's in it, of radius r and thickness dr is 4 pi r squared dr, and that's the shell over here that I'm thinking of in that picture. All right, we've got a little less than 10 minutes left. So what I'd like to do is to talk about how you can put together a model of a star using the equations that we've got so far. The key equations we have are the equation of hydrostatic equilibrium. We needed to know a way of calculating G within that equation, and that was G M sub r over r squared. And then we needed a way of calculating M sub r, and this provides it to us. And so why don't we kind of tie it all together? We'll still talk abstractly, but we'll talk about the steps that one does when they want to build up a model of a star. So to build a star model, with a desired rho equal rho of r, there's a lot of freedom in your star models. I mean, you can have all kinds of density profiles and so on. So you got to start with something. And in this case, we're going to say, hey, this is the density profile, rho of r, that I want. And I'm not going to specify it, but in the back of your mind, you can pretend that I did. You know, maybe it's, you know, sine r over r, or whatever it is. It's some function that as you go from the center to the surface, it decreases to a value of 0. And you can imagine that that's a given. We call these things profiles. So what do we do? Well, if you've been given a rho profile, you can integrate to get M sub r, right? You'd integrate from 0 to r of rho of r times 4 pi r squared dr. So you would have to do this integral for many, many, many different values of r on the upper limit of integration. But once you've done that, you've got, for every value of r you did the integral for, you have the value of the mass enclosed. So if somebody cans you the rho profile, you can figure out at any location within the star what the mass enclosed is. Then what do you do next? Well, you could rearrange dpdr equal minus g rho, because minus g rho is minus capital G M sub r over r squared times rho. And then that means that dp is equal to minus G M sub r over r squared times rho dr. All I've done in the last step is to multiply both sides by dr. And now I integrate. And so I might integrate from the surface where the pressure is 0. So that'll be my lower limit of integration. And if I'm thinking about the surface as defining where the lower limit of integration is, then this would be a capital R that I would integrate to from as the lower limit on the right hand side. And then to some arbitrary pressure, in the middle of the star somewhere, P. So to some arbitrary location, the upper limit of integration on the right would just be R. And I can't do any more without someone telling me specifically what rho of R is. Maybe they got to tell it to me on a computer in a table in tabular format, right? They list in column 1 the radius and in column 2 the density. And that effectively is a rho versus rho of R function then they've handed me. But someone either needs to give me a function or a table, and then I know rho of R, so I can put it in there. I know m of R because I've done this integral, maybe numerically. And so I know I can put it in there, and I can do this integral. And then I get, on the left-hand side here, this integral is just the pressure. And so what do I get out when I do this integral? I get pressure as a function of position. And so I now know not only rho everywhere inside the star, but the mass enclosed everywhere and the pressure everywhere. All right, well, we're going to finish by doing an example. This is similar to example 10.1.1. And so it's just going to give us some practice thinking about the equation of hydrostatic equilibrium, what it tells us, give us some practice thinking about what the interiors of stars are like. And so I guess one thing I want to point out is dPdr equals minus g rho. And so that tells you right away, if you plot pressure versus radius inside of a star, that the slope is negative. Slope is, I'll say, non-positive. That's one thing to note. Because G is always positive or 0, and rho is always positive, or I guess 0 at the surface. And now the other thing is, remember that G is equal to 0 at the center. So dPdr is equal to 0 at the center. So the pressure profile of a star starts out as a horizontal segment. It's a local maximum, and then it decreases. And then as you go to the surface, it flattens out again. And so there would be the surface, capital R. Here's the star of radius R. Qualitatively, that's what a pressure profile in a star looks like. And we know that just by looking at the form of the equation of hydrostatic equilibrium. And we're not going to get into a detailed model here, but what we're going to say is that a typical slope, which is the left-hand side of the hydrostatic equilibrium equation, is just the slope of this function. dPdr is something like, well, I've already told you the minimum and maximum radius inside the star. It goes from 0 to capital R. So as you work your way outward, the last value of R is capital R. The first value of lowercase r is 0. And now I'm going to define the central pressure to be P sub C. Now in the vertical direction on this graph, I see that I end up with a pressure of 0, and I started with a pressure of PC. So you know how slopes are rise over runs. So the rise is negative PC. It starts at PC and it goes down to 0. So that's a lowering by an amount PC. And the run is from 0 to R. So the slope is minus PC over R. That's a typical value of the slope. It's really the slope of some dashed line that connects, this point and that point. But somewhere in that profile, if not in 2 or more places, there is the curve is parallel to that dashed line that I just drew, right? So this number is an estimate of a typical slope dPdr. Now, if we look at the right-hand side of the equation of hydrostatic equilibrium, we can ask ourselves what a typical value for that is as well. And so a typical G times rho, I'll neglect the minus sign here. I'll suppress it. I won't bother to write it down. This is G m sub r over r squared times rho. And so G has a value always equal to G. A typical value of m sub r, I know we're out of time here. I'm just going to finish with this, is m over 2. A typical value of lowercase r is capital R, or r over 2, sure, just somewhere in the middle, and that gets squared. And a typical value of rho is m over 4/3 pi r cubed. And we are out of time for today, but to preview what I'll start with next time is we can simplify this and not worry about coefficients of order unity like 2. And we can set these two things equal approximately to one another. And what you find now is you have a way of knowing how the central pressure scales with the mass and radius of the star, because these two typical values should scale in the same way as one another. Are there any final comments or questions?
Is there a natural form for the density profile of a star, or does it vary depending on the makeup of the star?
It varies as to what the density profile is, and as a star evolves, that density profile will change. What happens is that when a star is born, it's not uniform in density, no, but it's more uniform at that point. And as it evolves, its core gets denser and denser and denser. And so a star might be born just as a rough sketch with some density profile that looks like that, but then as it evolves, it gets more centrally concentrated over time. And so, yeah, there's lots of functions that you can write down that in some approximation, in certain stages are, the density scales like sine of some constant times r over r. Yeah, so certain stars might have a density profile that look like that. But yeah, that maybe like a neutron star or a planet might have something that's like that. But there's no one function that describes everything. And we'll do this again. Same bat time, same bat channel.